So this is the second and final lecture about what we started yesterday. So far we have seen that granular materials show some interesting behaviors. So what we have seen is that granular materials show some interesting behaviors which would typically make it hard to classify them either as a solid or as a fluid. And as we will probably see today briefly through a movie, that they can also be described as gas. We talked about in particular the static aspect in some sense, with one demo involving with the so called fluid aspect. Actually it involves both solid and fluid like behavior, and we saw that the pressure in a granular bin saturates. We did a demo where somebody reasonably strong in our audience tried to push the sand and could not really bulge a balloon, which was supposedly a trivial task, and the reason is because your pressure saturates. So no matter how much pressure you apply at the top surface, your pressure in the container saturates. So essentially what we are saying is, if you have a sand filled in a container and you apply a pressure at the top, your pressure here is practically unaffected. Let me also take this opportunity to correct. So I had the axis notation incorrect yesterday. The reason I drew it this way to show that, so I interchanged the z and sigma zz yesterday. So what you see is that for near the free surface there is near hydrostatic variation, and then this thing starts to plateau. And so if you, so this is what would happen. For example, we did a simple analysis following Jansen's model, and this is what we could predict, that you will have a plateauing of the stress because of the wall friction. So the additional weight is basically being carried by the friction wall. So your pressure applied, the normal stress or the stress in the z direction gives rise to stress in the radial direction, which in turn gives rise to friction at the walls, and hence in some sense you get shielding. So if you apply additional pressure, depending on what value of pressure you are applying, your profile is essentially going to be like this, but you will end up getting this saturation. All right. Where does this profile in some sense meets depends on what is your z. So for example, when we reduce the amount of sand in the demo yesterday, which means that you can actually, so and if you apply sufficient pressure, it is possible that you see change in the stress. All right. So that is what we saw yesterday. So what we'll do now is we'll move to the next aspect. Okay, before we, so in this derivation we made quite a few assumptions. One of the assumptions was we assumed that the friction at the wall was fully immobilized, and that's a crucial assumption. In fact, if you, let's say if you just pour something in a container and measure the stress at the base, you may not find this pressure what you are expecting from the such Jansen's analysis. And the reason is because when you are deriving this, you have assumed that the friction is fully immobilized, which may or may not happen. And as all of you are familiar with, let's say if I have a inclined plane of mass m, block of mass m on inclined plane theta, you have some friction at the base. The friction force needs a minimum inclination before it gets completely functional, right? So to hit the limit, so your friction force F will always be less than or at max be equal to the friction coefficient that you have times the normal force, which means that when you are doing this analysis, this assumption that the friction force is fully mobilized at the wall will be valid only if you have done the experiment in a particular manner. So if you really want a good match with the simulation or experimental data, what is typically done in the experimental protocol is that you fill the container with a plate and then you move the base plate slightly, so that you ensure that you have indeed got the particles sliding at the wall and the friction is fully mobilized. If you are not doing that, you may not get the data fitting to the curve that you are predicting. All right. In fact, this friction force, the indeterminacy of the friction force, so the Coulomb's law of friction essentially tells you the maximum possible value of friction. All right. Friction can take any value, in this case depending on theta. All right, and I'm not bothering about the differentiation between kinetic and static friction, but you have this indeterminacy in terms of what is going to be the friction force. So which means you can have some friction force which could be less than this, and you may not see the predictions as you would observe. And this indeterminacy of the friction force essentially leads to a lot of phenomena which sort of seem pretty hard to explain in granular material. So for example, let's say if you had a, so imagine a classical situation which you have done in your intermediates, right, or even a fluids course. You have a container filled with liquid and you revolve the entire container with some velocity omega. You can do simple analysis either through momentum balance equations or you making use of a simple element of the fluid and doing force balances, that you should get a parabolic shape, right. That's pretty sort of easy. I'm sure all of you must have done it at some point of time. Let's say I want to repeat the same experiment in granular materials, and I did, because the derivation, all that you have to do is in the elemental analysis you just have to introduce friction, and if you do that you can predict what the shape should look like. I tried in my, I gave, this was one of the UGPs given to a student. We tried that, and this, the derivation is not at all a big deal, but then trying to reproduce in the experiments reliably was becoming a challenge. In fact, while doing this, if you know, we played with it a lot. If you just change the shape, so let's say if you got, so you do get some sort of dip at the base depending on how your system is, but your steady state that you will observe in a rotating cylinder of sand does depend on the initial configuration. And so without going into the details, essentially what I am saying is, if I have, let's say, if I am rotating along this, you will find a reason. So let's say so when you solve, you will again assume that friction is fully mobilized. So the friction being fully mobilized means that you have to go a minimum distance so that your friction forces, the centrifugal force is balancing the friction force. And so you will see a region in which, depending on what your omega is, your shape is not at all changed, which means I can maintain whatever shape I want here. Alright, of course it cannot go beyond the angle of repose, but there is a region in which you can define what you can sort of maintain your initial state given your omega. And after that you will see some, so if you assume that you have friction fully mobilized, you will see some variation followed by a near linear variation. Alright, but this derivation, when you are assuming this, you have already assumed that beyond this region friction is fully mobilized. Alright, now what I do is I perturb my surface, and I don't have those videos unfortunately. I perturb my surface. What I can do is, if I take a surface like this surface is also stable. What I am trying to emphasize is that if I have a rotating bowl of granular materials and it's rotating, and let's say if I poke it with something, I can get all possible shapes that you can imagine, and they'll be fairly stable as long as you're not violating this friction, because there is a wide range of possibility. In fact, this is something I think you must have seen, something like this. You must have seen a sand heap, pretty common, right? And you can find all possible shapes and various possibilities of shape or heap shape simply because the friction is independent. The maximum angle that you can get is in some sense governed by the friction, the law of friction, but otherwise there is a whole lot of possibilities. In fact, people have also attempted thermodynamics of granular materials, assuming that you have different states, and the compaction becomes then one of the sort of properties through which you would sort of like to explore, that in all the possible situations you can have compactions. Those compactions are one of the thermodynamic states that you can think of about. Alright. So before I move to this, I just want to show you this image which I couldn't show you yesterday. So because of this pressure saturation, what you see is the grain storage is typically done in tall columns, as opposed to, for example, let's say crude oil storage, which is typically done in containers which are wider and as compared to the diameter. And we talked about this, right? Because in the pressure, your pressure variation in fluid is going to be hydrostatic, and hence a taller column means a thicker column, which is not the case in case of grain storage. All right. So this is primarily about the static granular media, or the solid like part, that I wanted to talk about. What we'll do is now we'll move to the fluid like behavior. So we have done this demo before, so we are not really going to bother. So they can also behave like fluids or liquids because they take the shape of the container you put them in, and hourglass is a classical example, right? And so Not just that, they can also flow through a orifice. We did this demo yesterday, and they'll keep flowing in an hourglass. In fact, the flow rate seems to be independent of height, which means if you're measuring time, I mean the time is independent of the head. Your flow rate is independent of head, and so this is a linear time measurement device if you want to build with. If you had a fluid, let's say, then whatever you are collecting depends on your pressure head, and that's why a fluid hourglass is not that popular. I mean, of course you can always use it, just that you need a bit, either a calibration chart or something. So in this case, I mean, if you are measuring something for a particular time, I mean this linear variation ensures that we are going to get a constant flow rate depending, except when you are almost towards the emptying this. All right. So we did this, and we saw yesterday that this flow rate was independent of the height, right? So we had a container it had a base, a hole at the base or at the top, and I inverted it, and then we measured the flow rate for height, a particular height and 4 times the height, and we found out the flow rate is independent of the head, right? We also have this information which says that your pressure is also independent of head, and so there should be an obvious connection that you can make. Can somebody tell me what that would be? So your pressure here is not rho GH, right? Saturated pressure or sigma ZZ, let's say, since we have seen that this is rho G times lambda, right? And this lambda was basically diameter divided by some numbers, which are essentially sort of order 1 numbers. So what this tells you is that in a region which is sort of spanning almost, I mean order of, so the region close to the orifice, which is having a size almost, I mean order of the diameter, you have some variation, but beyond that everything is constant. And so you might want to try what you typically would do for a fluid, right? You would expect velocity to be proportional to, see in that case you assume that hydrostatic variation and you say pressure equal to root 2 GH. The velocity at the exit is, assuming Bernoulli's is 2 GH, except that now instead of the H, because the pressure is no longer hydrostatic, I can use this lambda and try some correlation. Is everybody with me? Is everybody following what I am saying? I am trying to connect the constant flow rate through our orifice with the constant pressure that we observed yesterday, and trying to see if there is a connection between the two, because that's an obvious connection as a fluid mechanics person somebody would like to make, right? So in a fluid, if you had a fluid container, you say that your exit velocity goes as root 2 GH because your pressure variation is hydrostatic, right? And so pressure here is hydrostatic if you really want to apply Bernoulli in some sense, like half rho v square plus rho GH kind of thing, and you get this kind of velocity scale. For this case, when your pressure is saturating, you would like to apply a similar relation, except that you would say that your pressure is no longer hydrostatic, it's some constant, and since pressure is constant, pressure is independent of height, you would expect that. So it is possible to propose, that we exit for, let's say, grains. So I am just trying to see if we can somehow connect to what we observed yesterday. You will get some V exit at the grains would be of the order of root of gravity into, instead of H, we can say that this is sort of lambda. I'm just, you want to keep 2, that's okay. But so this is going to be order of G raised to power half, and your lambda has, alright, I am again throwing this order 1 terms again. So lambda is your screening length or characteristic length, which depends on the diameter of the container. Yes, assuming that friction is fully mobilized. And so if you try to make that connection, I mean you will assume that this is what sort of makes your flow rate independent of the head, alright. So if you want to think in terms of the mass flow rate, that will go as area, which is your d orifice square, I am scooping the term pi d square by 4, right, multiplied by this term, which basically gives you g raised to power half, and your d raised to power half d here is of the cylinder. Everybody with me?
So why would d cylinder be important?
That's what I am coming to. So all that I am, so because you are not, all that I am saying is that you have a container in which there is a pressure saturation, and so the pressure saturation, if I assume that pressure saturation is what makes the flow independent of the height, then this is how one would like to proceed. Alright, is that clear to everybody? All that I am saying is, if that is the one way that you can think of, alright. It turns out, and so this possible way to think has often led to people write even in research papers that the head independence of the pressure leads to head independent flow rate. This is not correct. Alright. So simple connections that you would typically make from fluid mechanics may mislead you to get incorrect conclusions. In fact, what has been observed is, so let me just erase this. So what people have done is, in fact this was done something like 50 or rather 70 years ago approximately by Beverloo. So what Beverloo did was, he took a cylindrical container, alright, at the base there is a hole, and you put some sand here, and you measure the weight of the mass falling down, alright. You will have, what you do is you measure the mass just like we did yesterday, right. And what he does is he changes, so you have grains which are of diameter d, and you have this orifice which is of diameter, let us say capital D, alright. So now when I say capital D, that is what I mean by d orifice. D cylinder does not really come into the picture, and that is what I want to emphasize. What Beverloo found is that if you look at the mass flow rate, okay. So if you look at the mass flow rate, it turns out to be proportional to, of course, bulk density of the material, gravity raised to power half, and d raised to power 5/2. Now let me just put orifice here again. This is what you would observe if your orifice was really large enough compared to grain size. Alright. So this cylinder diameter does not seem to affect this as long as your diameter is beyond, let us say, 3 times the orifice diameter. So if you are beyond, let us say, the cylinder is not really very much comparable to your orifice diameter, then what you find is cylinder diameter has absolutely no influence. And in fact, so what Beverloo proposed was you can have something like some constant into bulk density, gravity raised to power d half, and so what Beverloo essentially did was he plotted m dot raised to power 2/5 so that you have a linear variation for different orifice sizes, alright. Or alternatively what you can do is, if you take a log of this, you will have log m and log d with a slope of 5/2, and that is what Beverloo observed. So if you plot, let us say, log of m with a log of d, what you observe is there is a linear variation, fairly linear variation, with the slope being approximately 5/2. The only difference being that this line, when extended, so of course you have measurement only up to some data point, when you extend this, so of course this is log, so it does not really make sense to extrapolate it, but it seems that it is cutting it at a value of orifice diameter which is not equal to 0. So you have some finite size at which you think so, and he proposed that a form of this would be, or rather is more appropriate. This is what Beverloo predicted way back in 1961. He did this for different kind of grains, sand grains, some cereals, poppy seeds, different orifice. So essentially this is the best that Beverloo could come up with, suggesting that one, your mass flow rate seems to go to 0, and this K value is, the value K is not equal to 1, and so this value K is typically between 1 to 3. So in some sense you have some finite size correction because of the fine particle size, which suggests that your mass flow rate goes to 0 but not at, so this K is not necessarily 1, you have some value. So if you had, let's say, just one particle diameter, you would, at least there will be some expectation that will probably give you some static region. So K less than 1, of course you can't flow, but K greater than 1 is what is repeatedly observed, and then this relation is valid only, so you're not really hitting all this limit, you're not really going to this 3D. So this relation is valid only for, the grain diameter should be less than 1/6 of the orifice diameter. So if you're having grains which are, let's say, more than 1/6 of the orifice diameter, you get jamming or intermittent flow. So if you're having large enough grains, you don't really get a constant flow that you would observe. You'll see flow happening for some time and then maybe it'll jam, may unjam if you push it a bit, and then again continue. So for a free flow regime, so this relation is valid for a free flow regime when your grains are smaller than a particular size. Beyond that, intermittency in the flow is observed. Please.
The diameter of the cylinder is constant in all the cases?
Cylinder.
In this relationship, the diameter of the cylinder does not.
So he tried different cylinders as well. It seems cylinder diameter doesn't play a role as long as your D cylinder is greater than, let's say, 3 times D orifice. So if your orifice is, let's say, not really very close to, so if you, the extreme case, you imagine that your cylinder is, the entire cylinder bottom is open, then it will of course fall under the influence of gravity. There is nothing that you are going to observe. So if typically if your cylinder orifice diameter is larger, is a factor 1/3 of the diameter, then it seems it doesn't really make a difference, and this number is not sacrosanct. Even if you go a bit smaller, you're not really going to see much of a difference. So that's what was Beverloo's observation. So okay, please.
So what will happen if the opening is not circular in this case? The opening
We'll come back to that. Good question. Please.
When cylinder does play a role, then how is the relationship like?
So it's possible to do some simulation experiment and get there. The thing is that in most of the real life situation, you would typically, so for example, imagine industry, you will typically have a pretty large container which you would like to work for few hours, which means the size would be typically, so of course yes, you can make a very tall column, but you typically have a pretty good, so in most practical situations you would typically want the size ratios are pretty off. So you can do some of the analysis there, but because there is not much practical use, it's there's no clear, one result that describes all that.
Or maybe the more practical one with the other one, when the ring particle diameter is much larger than D over 6.
Yes. So this is what has been the classical understanding of a Beverloo.
Can you spell this?
Oh sure, sorry. So this fellow is Beverloo, 1961. So here the one of the most commonly cited paper where he almost establishes that this is the correlation that you should use for a mass flow rate, and then the same relation can be modified with if you have a correction, if let's say, so why is this work important? So typically when you have, let's say, flow occurring through a hopper, you can have something like this, and then the hopper diameter is, let's say, D. So you will have some dependence on what is the material property in some sense, what is this half angle of the hopper in that case, all that happens is you get a correction factor because of what is the material, the Hopper angle, the other properties. So you can get some correction factor with it, but the essential form remains this, and that is why this is the most commonly cited, commonly used result.
Sir, in this case, d diameter of orifice is always greater than kd?
Oh yes, yes. In fact, it has to be greater than 6d. So the value of k is 1/3, but you don't really get data up to there. This data, because you want to have a free flow. So if you remember, we were doing this experiment yesterday. I mean, so you see a flow, especially when I tilted it, and it was getting jammed, and then if I tap it, it was starting again, right? So that happens because of a different region. But if your sizes are, so this is a typically when your particles are, or your orifice diameter is, let's say, less than 6 diameters of the grains, you're not really going to get a free flow. So what recently people have done is, so of course this is purely empirical, there's no, if I can say this, I mean there's not much theoretical this thing given behind, but since your area, so one of the ways this is popularly understood is, so one of the, so this term, presence of the term kd is typically explained by, let's say this is your orifice diameter, because you have a finite size of the grains. I mean the grain which is, let's say, sitting here will probably not fall through it, and so you get a finite size correction, and so the effective orifice diameter is not d but something less than that, and that could be something like, d minus kd, how you can sort of interpret it, but that's only sort of, I mean a hand waving argument, because though it makes physical sense, it doesn't explain why k is greater than 1, right? I mean k greater than 1 doesn't make sense from this picture. So there are issues with this, but it seems like this works pretty fine for, I mean, different kind of particles. And this value of the constant c, again Beverloo suggests, is typically within the range of 0.55 to 0.65. So the value of the c, the constant that Beverloo is proposing, is something between 0.55 to 0.65. Please.
For some information about the saturated velocity, as if like it scales.
I'm just going to do that. Thank you. So, I mean, if you look at this, even if you buy this argument that there is some excluded region, and then you have a effective orifice diameter which is smaller, so your effective orifice diameter square is taken care of. What it tells you is that your mass flow rate is density into velocity into area, and so your velocity has to be square root of gravity times the square root of this orifice. Is everybody with me? So what this says is that your V exit, please.
What is this K called?
Oh, this is some Beverloo constant. So this is Beverloo constant, and this is the fitting parameter. There's no, I mean, there's no sacrosanct name for it. So this V exit then for the grains is of the order of, and D again I'll just highlight that this is orifice size, which suggests that essentially you are getting the velocity scale is essentially coming because of this. So if I have an orifice like this, if I have an orifice like this, your velocity scale is something like what you would probably, for example, expect if you had, let's say, a free fall of a particle through some some arc. So I mean you can get the exact number there. So if you look at the average velocity, this will be something like 0.74 if you want, and so that just suggests that something like this may be able to explain it. Essentially you are getting a region in which particles are experiencing almost free fall, and hence you get velocity of equal to root 2 gh, except that your height keeps varying, and so when you average it out you should get this. Is everybody with me? And
what happens to the factor minus kd in that expression?
so you just assume that this is your D effective. So this is, I mean if so, I'll come back to why this is coming. I mean I'll probably. So if you look at this, so you're saying instead of D you bother about D effective then, and then you just think of it as a free fall arc, where from, so this is a region in which particles are very slowly moving, all right, and you, for a theoretical this thing, you assume that the velocities in the slow flow regime are 0. You somehow manage to come to this free fall arc, and then you have the entire gravity pulling you down and you just fall through, all right. So if you use that, such a picture, I think I should have a slide showing that. Okay, yeah, so I'll just make my life simpler. I have to not draw a figure and I'll just write the expressions.
But does K depends on type of ring?
Yes, so K in some sense is a material property, is a fitting parameter, it does. So now this derivation that we are going to talk about is due to Hilton and Clary, and that's as late as 2011. So this was 1961, Beverloo. Some ideas about using, but I mean some simplistic derivation suggesting that yes indeed it is possible is few years ago, and what essentially they suggest is that you assume a free fall arc, and the free fall arc, I mean, is assumed to be hemispherical in shape. So this is the hemisphere of diameter d. Before that, particles are having negligible velocity. Once you reach there, you fall under gravity, and so what you can do is you can look at a region between r and r plus dr, and so you will get a ring of the particles which will fall through height h, which depends on r, right. Just speed it up. So essentially what you are saying is, so this h of r, as you can quickly figure out, this h of r is going to be, so this is your so we are looking for this height, this is going to be capital R, this is small r, so h r of is going to be, right. So you have this is r, this is small r, so we are talking about this height, that just becomes this, and so then your velocity falling for the particles which are at that value of r is simply root 2g h of r, which essentially becomes square root of 2 times gravity times r square minus r square raised to power 1/4. All right. So your mass flow rate, now what you can do is you can calculate your so mass flow rate is, you have, so the area available is 2 pi r dr, right. That's your area through which the particles are going to fall. All particles in this area are going to have velocity vr. Sorry, let me just, right. So that's your volume flow rate. You multiply it by the bulk density, assuming it to be constant, and then you integrate this from r equal to 0 to r equal to capital R. All right. So if you just do that, I mean the derivation is relatively simple, I am not really going to spend time on that. What you are going to get is essentially something like pi over 5 bulk density times gravity raised to power half times, so instead of r I will do d by 2, and d is my d effective. This is what the derivation gives you, and this constant pi by 5 is essentially something like 0.628, which is well within the range that Beverloo predicted, something between 0.55 to 0.65. Please.
So are there any limits on particle diameter of this theory?
Well, this theory is just trying to say why do you get that number between 0.55 and 0.65, that's it. That's it. The limit is in the experiment itself. You can't go, so grain size cannot be greater than d by 6. You will start getting intermittent flow. Your flow will not be continuous. In other words, what I am saying is, if I had a slightly coarser sand in this box, you will not see it flowing despite I turning it up, tilting it up, or it may flow for some time and it will stop again.
What if finer?
Finer will flow. Finer will flow. So the only limit is, and I erase that, the only limit is just, So your grain diameter has to be less than d by 6, alright. And when you are doing this, see, we are assuming that air drag is not playing any role in this theory, and that happens in experiments as well. There has to be minimum size as well, so that air drag is negligible. We have already kind of had that size, but typically what Nederman proposes is that you should have something like 0.4 mm or so, so that air drag is not really playing much of a role. Again, this number could be 0.35 or something like that, but essentially if you are talking about, let's say, particles greater than, let's say, 0.4 mm, Beverly correlation seems pretty good, and you will get a continuous flow unless you go closer to that. The value k being dependent on, for example, sand will give you a value of k slightly higher, spherical particles will have k value closer to 1. So that is what sort of Beverly suggested, and this simplified theory by Hilton and Clary suggests that yes, indeed this makes sense, I mean, at least there is a way you can figure out that number.
So ultimately 0.55 to 0.65 depend upon the shape that we have choose.
Of the?
That we have choose over there, hemisphere.
Yes, so you are right. So now why hemisphere?
Yeah.
Why hemisphere? What is so sacrosanct about hemisphere? So what people have done is, I mean, you can actually choose other shapes as well, right? In fact, now that computer simulations are possible and you have high speed imaging, people have actually done experiments and see if you want to look at a sort of something like a free fall arc or whatever, if there are two different regions, how does that region look like? So it does look qualitative, looks like this.
This shape depends on the shearing effort of the grain.
The shape depends on the shape of the free fall.
Shearing effort of the grains between the grains.
The shape of the arc, you mean?
Yeah, like the effective shape through which it falls.
No, you are talking about this d minus kd term or this arc shape?
D
Yes. So k does depend on the shape of the grains, of course. So see, so for example, if you have cohesive grains, what people have done is that this k will be a function of the cohesion between the particles, and you can still see all that this is saying is that here is a form. Now you can play with independent terms and do more data and get this, but this is what the basic form looks like. All right. However, when people have done experiments and also simulations, and as he rightly asked, there is no reason why hemispherical arc should be the only way, right? In fact, when people have done some experiments and they suggest the shape is actually parabolic. The shape is more closer to parabolic, and if you're looking at the velocity profile that you are going to get because of the free fall, I mean, profile gives you something like this. If you take a parabolic shape, you will have a slightly lower profile, and so this number will be slightly lower further. So you can so people have done simulations and experiments and shown that the shape is actually parabolic, resembles more to a parabola.
So indeed, simulations confirm that there is a free fall region?
No, so I am coming to that. So they confirm that if you want to identify a region near the exit, it is possible to see a region, but that is more like a parabola rather than a hemisphere. All right.
Sir, can we reason like if you are trying to pour the sand on a paper and the shape of the sand which is collected, if it is related to an arc or parabola, can you predict some velocity of the?
So if you pour it on a paper, you will get a cone.
Yeah, that.
So that you'll get a heap. That's what, and that's so you can get multiple possible shapes, right? As we said, but in the ultimate shape, the maximum. So with a dry grain, the best artistic design that you can make, a simplistic design, if I can say, is a good-looking cone. You add some water to it, cohesion becomes important. You will make sand castles. If not castles in the air, you can definitely make castles in the sand. But dry grains, all that you're going to get is a heap, a conical heap. All right. So
beyond this, I mean, derivation or supporting this kind of experimental result, does the theory have any other sort of significance?
well, so I'll come. I wanted to skip that, but since you have said it, so this free fall picture has fundamental problems. It says that you have a stress discontinuity at the free fall arch, right? It doesn't make sense. So what people have done is trying to sort of disentangle that paradox. People have done simulation, and what you find is if you look at the stresses, your stress doesn't really show a jump here. You don't see a jump in the stress as you would expect, right? So you take the collisional component, the contact force stress because of the contact, and the other one is because of what was being neglected in Jim's lecture yesterday, the streaming component. And it is the streaming component which basically says your grains are sort of have got more freedom to jiggle around in this region, and that's not happening there. So when you say that they are having zero velocity and all, that's not correct. So I'm just so first your shape is, so you get a reasonable number but the shape is not correct. Then you are assuming a constant bulk density, that is also not correct. As you can see, you'll have densities relevant sort of comparable to, so density profile is qualitatively similar. You have more high density region here, low density region here. This is velocity, but density also looks qualitatively similar with rather than square root it goes 1 raised to power 4. So, and what you also see is, if you look at, so by the way, before I people have also tried something like a spherical section. So just like somebody asked, I mean, why Hemi? If you look at this thing, you will see the flow primarily occurring in a zone, in a region. So you'll have not much flow. This is like a static region, and then you have a flowing region, somewhat little flow, but it's flowing. There's virtually no flow here. And so people said, well, we can think of it like a spherical arc, and the particles are free falling in that region, and you can predict those. So all that gives you a number which sort of compares and depends on few things, but this seems to be sort of and this is to be the simplest one, because your particles don't really fall this way. They do fall vertically, they don't really go in the radial direction as you would typically imagine them to go. And then this free fall arc shape is sort of hemisphere, and as you can see from the figure, the parabola is relatively closer to hemisphere. So simplistic assumption, good enough. If you put parabolic assumption, you will again get a number which brings it again in the same regime. However, detailed simulations show that actually this, so I mean the only reason I am trying to emphasize this is what you are talking about is 2011 and this thing is 2013 or so. So we are talking about things happening so recently, there is so much interesting stuff still remaining to be explored in this broad field. What people observe is that if you look at the, so let me just sort of try to draw a, so if you look at the effective acceleration, alright, of the particle. So when your particles are flowing, you just, let's say you look at the center line and you follow the particle and look at the effective acceleration of the particle. This picture tells you zero velocity, negligible velocity, or if at all constant velocity, zero acceleration, and then gravity. So what this picture suggests you is something like this, alright. That's what your effective acceleration is going to look like, right. So if I am coming from this, zero acceleration and then free fall under gravity, this is what it should look like. Experimental data, however, suggests that this is not the case. You see something of this sort, and even slightly acceleration slightly higher than gravity in some cases. And if you, I mean, so there is actually a lot of this thing, but this is how it sort of plateaus. But you can still, we could do this analysis, because simply if you approximate as a line, essentially all that you are saying is the effective velocity, which is integral a dt, area under curve. I mean this, so this will also be invalid in terms of if you sort of replace it by time. So you're saying that effect area under curve is, I mean, remains same. So if you make a free fall kind of assumption, you are still, I mean, at least for all practical purposes, you will get what you are looking for. There are more sort of details involved, but what I want to emphasize is, despite all this done, this free flow, now people have started bothering. So if you want to see a arc kind of a structure, you can see, at least in terms of, if not the collisional stresses, in terms of kinetic stresses, there is some region present where things are very different than what is happening above. And so there is some region where an arc like structure is existing, alright, not in the traditional physical sense. What people have also tried is, which we tried yesterday, what if I had a hole not at the bottom but at the side?
How do you, from that picture, how do you know that there is an arc?
No, not from here. No, I am saying the arc was from the kinetic and collisional thing.
But is there some computation?
Yes.
So you haven't shown it.
No, I am not put in there, but so because somebody asked, I was trying to skip that, because so what people have shown is that in this region you have kinetic stresses are sort of, you see if you plot the kinetic stresses, then they have this huge variation in the kinetic stresses along the center line.
So potentially that should have been spotted also from a description of the flow velocity. If I was to look at the velocity field, I should be able to see the change from
No.
dense flow. You can't spot
No.
it from there?
Well, I mean, so if you look at the accelerations, you see an accelerating regime all the through. So so you have your particles actually sort of, I mean, starting from a zero acceleration, they accelerate all the way through the center line. All right. When you're looking at the stresses, the only thing which suggests like a structure of arc, so you can look at the velocity and all other things. All right. You will have a velocity which is primarily varying in this. No, your velocity will be primarily varying in this and all. But the idea that you have a free fall arc.
No, I was just trying to say the free fall arc is basically a region where the flow field behaves very differently from the rest of the material.
Yes.
I'm wondering whether the ability to spot that special region depends on my being able to extract kinetic stresses, or can I also see it just from the kinematics, just from the flow?
From the flow also it is visible. Yeah, from the flow also it is visible. But if you look at the collisional stress and all, you don't see that this is the region where, so the collisional stress sort of, would suggest you that you have a continuous variation. So if you are assuming a free fall arc, everything is falling under influence of gravity, then you don't expect any significant collisional stress here, right? So what people say is that in that sense, you have a stress continuity. There is no stress discontinuity in that sense. And so that approaches which people have tried is not going to work. Only thing that is going to work is, not work. So what people have done is that there is some change in the streaming component of the tensor, which essentially says that, I mean, you're thinking in terms of simple free fall arc is probably not good enough. Is not good enough. Because the arc, when you say it's a classical arc that you will typically imagine because of the structure and all.
I was taking a far gentler view of the situation. I was just trying to say whether there is a region where the velocity field is
Yes.
much more rapid than the rest of the thing.
Yes.
And if that region is somewhat like this parabolic cap,
Yes.
there is such a
Yes. So there is some region like that.
there is
So
some
that's-
region, and that is within how much percentage of root 2 GH, I guess.
So that's what I'm. If you look at the, I mean,
From the computation, from the numerics, if you were to
yeah. So it's root 2 GH 1.07 to be precise. If you want to look at that PRL paper in 2012. So it's very much that. It's very much the same. So, but again, that velocity which you are comparing, or that they are comparing, is only here. So looking at the velocity in this zone.
what I was going to say is that looking at all the exit velocities there, you back calculate and find out.
That's what. So and that is what gave the parabolic arc. I told that in the beginning. That is what gave the idea of this parabolic free fall arc, if at all there is one. Please.
So if this is true, I mean, the free fall arch.
By the way, I mean, I think I just want to say that this is what has been the recent understanding. This thing shows that this is not true. Free fall arc, you don't need a free fall arc, because, and if you let me complete, if I had a side orifice, I will still again see a similar correlation. The exit velocity will still be root g times d, order root gd.
That's because that's the only dense scale you have.
Precisely. So it is a dimensional necessity of the problem. You don't, so you can try sort of, so this is what sort of, we are slowly building up. Your flow is very complicated, there is no way, so your flow is in this direction or in whatever direction, gravity is in perpendicular direction. So all that, and this is like, I mean, this is probably 2016 if I'm not wrong. So you have a horizontal orifice and you observe flow, you still get, so your correlation remains more or less the same, except that this constant becomes different. And in this case, please.
But so now can we say that this theory is not true? I mean, it's not valid.
Well, so that is what.
My argument was,
Yes.
if this were true, then actually it would reduce the computation expense significantly, right? Then we would only need to focus on this particular area, I mean, a zone.
So that is why, I mean, if you think in terms of the flow rate through a hopper and all, and they are pretty much calculated by Weber-Lewis correlation. You will have some correction factor. You identify that constant for your material, and that's how it has been. If you have a hopper which is tilting at an angle, your material is different. You add correction factors based on that, and that is why it has been sort of, I mean, surviving for so long. It has been surviving for so long. And in this case, I mean, you see that the velocity scale again this. The only thing that changes is your constant of the proportionality. The only interesting thing being that your flow rate also depends on the container thickness. Okay, let me repeat. So if I had so my container thickness now seems to influence the flow, right? Which was not the case. So if I had a hole here, whether my container is this thick or that thick, unless you are really attaching a pipe there, which basically the grains start, so when you have no slip at the air drag becoming important, that's a separate region, but otherwise you don't see much of an influence of the wall thickness. In this case, you do start seeing that.
Is it the lip of that orifice that would matter, or the thickness, or the lip?
So yeah, you can have different shapes. So essentially, I mean, let's say, so what, I mean, so the initial set of data that's suggested, we are sort of, sort of looking at it in a bit more detail. I am looking at it in a bit more detail. What you're essentially going to say is, I mean, I can make different shops, I mean, kind of this thing. What essentially is, if your container is really wide, and let's say for the time being just consider this horizontal one, what is happening is, if your material is flowing out from here, let me just make this figure a bit larger. So I'm just zooming out this region, all right. What you're seeing is, and your material is going to flow through here. All right, your material is just going to flow through here. So if my container was, let's say, of 0 thickness, which means I had absolutely such a tiny thickness, let's say, which is barely a grain diameter or so, my material will typically be flowing along some direction which is be typically governed by its angle of repose. The moment I increase my thickness, this fellow sort of, let's say, this fellow encounters a region which makes it sort of form a heap, and only some relatively smaller area is available, which means that if I make it container thickness big enough, this will completely block it. I'm sorry, it has to be, this will completely block the flow, and you will see no slip at all, no flow at all. And this is something, if you have, I mean, if you have happened to see a typical rice storage thing in the village, you typically have a, I mean, a container, jisme side mein they have a hole, and they put something in there, so that, I mean, if you want to take it out, you just remove that, collect some of the grain, and sort of, show it to this thing, and then close it again. So this is like a nice way, if you want to call. You don't have to make the container thick. What you can do is just attach a horizontal pipe, all right, and you can control the flow rate in relatively sort of, smarter fashion. It seems like people are doing it in the villages, all right. So, well, I did not plan to spend this much time on this flow through orifice, but that's okay. So what we'll do is, we'll just now, I'll probably just show you one regime which is about the granular gas. So now if you look at here, we have this is a video from YouTube. You have a vibrating base. Container has a base which is vibrated because of this thing, and you're vibrating it pretty fast, and your grains now are now behaving more like a granular gas, as you can see from here. Oops, okay, so here is what you see. So this is the size that's vibrating, and your grains are going there, and you have, the density is pretty low, the grains are going, just colliding there and bouncing back. And this is the sort of, gaseous regime where, I mean, the initial kinetic theories were sort of, attempted based on this picture, and now, as Jim has told it yesterday and will be sort of building upon it, it's possible to sort of extend it even when you have much denser flows, all right. So with this, what I'll do is, I'll show you this movie before I move to something theoretical. So now the good or the bad thing about these materials is that you can see all this solid, fluid and gas-like behavior in as single a situation as shown in this video. So this adventurous fellow goes on there, snow sitting there like solid, starts to flow like liquid, traps this fellow, which is okay, he deserved it probably, and it's flowing faster and faster, going like a fluid, and you have something like a gaseous clouds of this thing building up, and your adventure can also affect people who are watching there sitting quietly doing nothing. All right, these two people were lucky to escape from that, and I see some faces really angry that why do you have to kill people to make a point. Well, they don't. Let the cloud of this snow go away, and you will see people walking around. Can you see some people walking? No? Okay, so maybe I trimmed the picture. Okay, you can see there. Okay, they're here. So nobody is killed. No hinsa is done here. All right. So essentially, what we have sort of tried to see so far is that these materials can behave as solids, behave as liquids, behave as gases, and these three scenarios can occur in regular situation when you have, let's say, flow occurring from in a heap or in a hopper. So now this the slow flow regime, the more details about that probably coming from Mohr Coulomb theory and Drucker pressure. So that is sort of in some sense the plasticity theories and the soil mechanics. Those are one sort of very active domain. The other extreme, which is the rapid flow, dilute flow, your granular gas regime, that's sort of again another very interesting area of research, which will be, will not have time to look about. But this, the regime which is the liquid like regime, the dense flow regime, that because many granular flows in practical situations belong to this regime. So you have a, when you have flow occurring through, let's say, even a hopper, if you look at the close to the where your flowing region is, your packing fraction are not really very close to, they are of course far from the random close packing, which is what you will have probably in most of the other part. But in the flowing region you have packing fractions typically, again I am talking about monodispersed spherical particles, something between 50 to 60%, alright. And this regime was sort of not so easily describable by the kinetic theory part and the slow flow part. People have attempted trying combination of them in different fashion. One thing that has seemed to work reasonably well for a significant number of situations, still have a lot of questions to answer, is what is known as the viscoplastic rheological model for these materials, alright, and that's what I will be briefly talking about. So in this regime your grains are interacting not only by sustained frictional contacts but also because of the collisional contacts. The streaming part probably is not so important as Jim told yesterday, so we can, though it is present but it is not that significant. And so phenomenologically essentially what happens is, let's say if I have a collection of grains or an inclined plane, my flow will not start till so if I keep increasing my inclination angle, the flow will start only beyond a minimum inclination angle. Once I surpass that inclination angle, you will have a flowing layer which will have sort of depending on what is your base property, you can have shearing happening in the entire layer. And so that suggests that you have a flow threshold that exists. Beyond that flow threshold the flow does not occur, and once that happens you get a shear rate dependence, which is like a classical, which is more like a suggesting a viscous behavior. And so what people have attempted is this, what is initially termed as the frictional granular rheology. Let me just make sure that I am not really skipping anything here, okay. And so the way to think about flows in that dense regime is as follows. What you are looking here at, so let's say, let's consider a simple shearing flow. You have collection of grains, alright, which are between two plates. You have two plates, alright, put grains in between them, and you compress it by a, let's say, top pressure, pressure on the top plate is P, and then you move the top plate. This is the like typical shear flow experiment that you will do in a fluid. The only thing probably you may not be too much concerned about is this pressure part, alright. So in this case, so we are talking about dry grains. So what we are saying is you have, so think of sand or glass beads between two plates, alright, make a sort of band of them, let's say very little effect of the front wall for example, and you have a top plate which is moving, you apply some pressure on top of it and then you move. Once you move, this is the entire material in this can move, and this is the canonical sort of standard typical plane shear geometry that you can generate. And that something came up which can then be understood again in terms of dimensional arguments. So you are talking about shear flow of particles which are confined under a pressure P. If you assume that the system is really large, which means we are not talking about few grains, you have a rather large number of grains, so that the grain size itself becomes unimportant. So for example in here, if I had a very large width of the orifice as compared to the particle grain size, then that is the only relevant length scale that you have in the system. So we are making this assumption that my thickness of the layer is rather large, so that the only length scale in the system is grain. So grain diameter is the only thing that is important. You are not bothered about the system thickness, right, which you would expect for any realistic rheology. And the other assumption is that your particles are rigid, which means when you are applying pressure, your confining pressure is much smaller than the Young's modulus of the material, alright, which seems to be valid in most of the cases that you will typically deal with in industrial or real life scenarios. So if you take that, your system essentially has grain size, the mass of the grain, or if you take care of the size in that, you have the grain density that is playing a role. Your confining pressure is the only stress scale available to the system, because there is no, you have a rigid grain, so there is no other stress scale, and you have a shear rate, which is gamma dot. So you have 4 parameters, the dimensions are only involving m, l and t. So essentially what you get is the system is controlled by a single dimensionless parameter, and that if you make a combination of this rho p, d, p and gamma dot, essentially that or powers of this number is what is a possible scenario. So you can have, for example, this gamma dot d over square root of pressure divided by the density of the particle is what people call as inertial number, is the key parameter, is the key non-dimensional number which determines rheology in that regime, in that dense regime in which the slow flow regime, the more Coulomb theory and plasticity theory, soil mechanics are not very helpful, and the kinetic theory is may or may not be helpful, alright. So there are efforts to push it all the way here. And so the physical way to think about this inertial number is that your system has, because in the plane shear you have a macroscopic time scale of rearrangement, which is simply coming as inverse of the shear rate, and the other time scale which is because of the microscopic rearrangements of the particle. So you shear the particles go on top of that particle and then fall down, and so that microscopic time scale is the time scale that you will typically get, for example, is the time scale a particle will, for example, take to move by its own length scale, its own size, under a confining pressure P. And if you don't think so, what you can write is, if you write the equation of the motion of the particle as mass times d2, let's say this direction of y, d2y over dt is your force acting on it. Since it's occurring under the influence of pressure, Fy scales as Pd square. Your d2y over dt square would be the diameter of the particle, that's the length scale, divided by some t, and your microscopic time scale, we do not know what that is, square, and then your mass would be rho p d cube. So if you just put that in this equation, you will get the microscopic time scale as diameter divided by square root of pressure over this thing. So a way to think about this is like your square root of pressure over density is like the velocity scale for falling, and this is the size of the grain, and so that is a microscopic time scale, and it is the ratio of this microscopic time scale to macroscopic 1 over gamma dot, which is what is defining this inertial number, and that seems to determine the rheology. So from dimensional argument, since you have already ignored the Young's modulus of the particle, right, so the pressure is the only length scale available, this is the only dimensionless number available, so any other component of the stress, for example the shear stress in this case, will have to be proportional to the pressure, and the proportionality constant, which let's say from Coulomb theory or coming from that you have some effective friction coefficient, will can depend only on the inertial number. So you are saying that you have a shear stress is related to the confining pressure by means of a effective friction coefficient, and that friction coefficient is not constant as you would, for example, have if I am pushing this block or book on a surface, but since you have your grains are now colliding and undergoing through frictional contacts, you will have a friction coefficient that depends on this non-dimensional number, inertial number. What this also ensures is, this dimensional argument suggests is that your packing fraction of the grains, so by packing fraction I mean how closely packed my particles are. So the packing fraction phi is essentially volume occupied by the particles to the volume of the system, alright, and so 1 minus phi is your void, fraction of the voids present, will also depend if at all on anything on this inertial number, alright. And it seems like, so this has been tried to, people have tried this in different configurations. In many simple canonical configurations this seems to be valid. So what you are plotting here is, if you do so these are simulation results, and then people have done some experiments as well. Essentially what you are plotting is the shear stress to the pressure ratio on the y-axis as a function of this non-dimensional number, which is gamma dot times particle size divided by square root of confining pressure and density ratio divided by density, and you see some non-linear variation in this effective friction coefficient. So your effective friction coefficient is rising from a minimum value, which is probably what you would expect, right? If you have two solid surfaces in contact, let it be many solid particles, and you try to push, you'll have a minimum value of friction coefficient beyond which you can't really see any motion, right? And once that motion starts, you see a non-linear variation on this effective friction coefficient, and that does seem to sort of depend only on this inertial number. All right. So people have, you can do this kind of simulations or experiment in different geometries and try to propose a empirical form, what kind of equation can sort of capture this behavior. Poliquin in France suggested this variation, this particular form, suggesting that you are starting from a minimum value of mu1 going to a maximum value of mu2 with the variation being 1 plus I naught over I. So at very large, at I equal to 0, this number essentially becomes infinity, so this term is off, you have mu equal to mu1, and when I is very large, this term is 0, and so you have mu1 plus mu2 minus mu1, essentially hitting a maximum value of friction coefficient, effective friction coefficient to be precise. This is what was sort of is the proposition by Poliquin. So now this model has then been extended to so since this is, you can extend this to 3D, full 3D viscoplastic rheology, essentially saying that the shear stress is again sigma minus some pressure term, and the shear stress is then governed by minus 2 times viscosity times this gradient of the velocity tensor. The viscosity now, so this is in some sense you're writing a viscoplastic rheological model. The viscosity now is or the effective viscosity is some mu I times pressure divided by your magnitude of the second norm of the gamma dot, the shear rate tensor, all right, and that is valid only when your shear the second norm of the shear stress tensor is greater than minimum that you require, so mu1p. Otherwise your viscosity is infinity. So that's like a typical viscoplastic formulation that you would have, and people have tried this over a, let's say if you have an inclined channel where the side walls are also playing important role, so you have shearing not only in the vertical direction but also along the box, it's possible to capture the variation in two directions. So you have shearing in more than one direction, and it's possible to capture pretty good match. This is Poliquin's Nature paper in 2006. All right. So this is the sort of one rheological way through which you can try to model these materials in that particular regime, in that sort of packing friction between. So if you go back to this figure, sorry, you're talking about packing friction inertial numbers which are not too large, and I'll probably show it in the next slide. I'll just skip this for. So your packing fraction, so for example if I do a simulation, if I do a computer simulation, and forgive me for skipping the details about how do I do the simulations, but believe that I can do it. We have if you look at the velocity profile over an inclined plane, as expected your velocity profile keeps increasing as you keep increasing the inclination angle. The more you tilt your flow, so of course you will not have a flow, you will not have any flow beyond a minimum angle, and so then beyond that you see a flow, and the velocity profile then goes something like this, and this, if you want to have a functional sort of dependence, this goes as y raised to power 3/2 rather than y raised to power, for example if you had a Newtonian fluid you will have parabolic profile y square, right. What you are having is y raised to power 3/2, that's popularly called Bagnall profile, because Bagnall in 1950s first proposed a constitutive law and suggested why this could make sense. Your packing fraction, as you keep increasing the inclination angle, your packing fractions keep decreasing. So this is somewhere between 0.58 to something like 0.52 is what you are looking at here. So this is between theta 22 to 28. So there is a range of inclination angle at which this thing is going to work. Let me just use the board so that I can make a bit more sense of what I am showing here. So if you write the momentum balance equation on an inclined plane, your momentum balance equation for a steady fully developed flow with a constant bulk density assumption reduce to your x momentum balance reducing to shear stress, essentially turning out to be the component of the weight of the layer in the flowing direction, and the pressure being the component of the weight in the y direction, alright. And then if you just assume that at the free surface you have no shear stress or pressure acting, you can just get this shear stress and pressure simply as, I don't know, I am calling it tau xy, should be tau yx. So if my density is constant, which seems to be constant across most of the layer, my packing fraction, which is my density, which in some sense is a representative of density, seems to vary very little near the free surface and the base, but in most of the region it's constant. So I can assume that the constant packing fraction or constant density is a good assumption. So this essentially comes out to be minus rho bulk g sin theta times h minus y, alright, and the minus sign is because the way we have chosen our axis, alright, and your pressure is going to be rho bulk g cos theta times h minus y. What this tells us is that if you look at the magnitude of shear stress to pressure, which is our effective friction coefficient, right, that is how we are defining it, is going to be equal to tan of theta. So for the inclined plane flow, steady fully developed inclined plane flow, given the model that we have, this says that for a given inclination of theta, tan theta is going to be equal to the effective friction coefficient. And since we know that your mu I starts from a minimum value and goes to a maximum value, at least that is what the popular knowledge is as of now, what it says is that if you are doing a chute flow, you are going to get a minimum angle at which your flow will start to begin, right. Below that your tau is going to be less than mu1 into p, and so you will not have any flow. So your theta minimum is essentially tan inverse mu1, and then as you keep increasing inclination angle, you will, so I am not plotting the results for close to this, that number turns out to be around 21 degree in this case. Please.
Why monodispersed particle? Means two slides back there was assumption, I guess, that it works for only monodispersed particles.
Yes. So I mean that is how it was proposed. So there are extensions available. If time permits, I will go there. But right now, because it was proposed for a monodisperse, that is why we are talking about this.
And again, for thin flow, it doesn't work.
So I am coming to that. So, but this is what you have as of now. All right. So you have a minimum angle at which the flow begins, and then there is a maximum angle, which supposedly is equal to tan inverse of maximum value of mu that you will find, and you will get a steady flow in this entire zone. All right. If you look at these results, I mean they do seem to sort of make sense. Your velocity profile, what this theory predicts. So your mu I is equal to tan theta. For a given theta, you know what value of mu I is. From that mu I, you can calculate what your I is, and this inertial number then is also helps you get the packing fraction. I will show you that, and so you can actually predict all these profiles, and they seem to match pretty well. And we are plotting here, for example, let us say thicknesses close to 40 particle diameters. And so if you, let us say if I do these simulations and plot the effective friction as a function of inertial number, which is gamma dot d over square root of p by rho, I do see this kind of, I mean data. I am doing it for 20 particle thick layers and 40 particle thick layers, falling more or less on the same graph, and this description seems to work pretty well with the model parameters, which are, of course, since their parameters have to be fitted from the model, turns out to be okay, not 21, 20.16 and some maximum angle 37 or something, and you have a characteristic I naught value which jumps into the model. In addition, I did not show this before, your packing fraction seems to decrease linearly as you increase your inertial number. So inertial number in some sense is a scaled shear rate, keeping everything constant, and so as you keep your flow, I mean keep increasing your shear rate, your packing friction keep going down, which is actually can be seen here, right. Your velocity increases, and if you look at the height of the layer also keeps increasing slowly. So layer is dilating, because the variation in the packing fraction is something between 0.6 to 0.45, you don't really see such a huge change.
Is there a physical interpretation for the characteristic inertial parameter?
Not that I have seen so far. And in fact, our recent results show that even mu2 has no physical significance, because this proposition that it saturates is incorrect. And so what is possible within the limited regime that this seems to work well. Before I go there, I should highlight this, that this seems to work pretty well for reasonably thicker piles. But if I showed you data for 20 particle thick layer, right? If you do the simulations, let's say for 15 particle or 10 diameter and thick and 5, the thinner your layers are, the more you deviate, the experimental or simulation data deviate from the theoretical predictions. So despite being able to capture few things, it does not explain flow over thin planes. And not just that, if you look at the flow threshold, so if you look at so we said that we will have a layer of, let's say, a minimum number of particles, a layer of, so I have a inclined plane and I make it slightly rough so that my particle can at least, and I keep tilting it. This is my height of the flow. So if I look at the minimum and I have a theta here, what people have observed is, so this theory predicts that the flow threshold is at a particular angle theta min, no matter what your height is. And this seems to be correct if only you had very large thickness of the layer. So for very large thickness of the layer, you have more or less same value of theta, but then as you come closer, you see a variation in the minimum thickness required for the flow to begin. So your flow threshold in that sense is not independent of the layer thickness height. This is something that this simplified model fails to predict. All right, and this essentially suggests towards non-local models, because so essentially what you're saying is that the rheology of the flow is not only determined locally what is happening, but also something which is, so the length of the bed is going to make a difference, and that, if you want, can also be seen from these results. If you look at the slope of the velocity profile near the free surface, or specifically this shear rate dvx over dy, they are not close to 0. At the free surface, the shear stress, I have it, goes to 0, but the shear rate remains finite, which suggests that there is something not, so this doesn't explain, and of course, so when we are applying this, we have assumed that this bulk region is what is dominating all across. You do see evident differences near the free surface and the base. So there are limitations with this model. Well, when your packing fraction starts to deviate significantly, that's all. It's not. So for this case, for example, if you look at the packing fraction, you have more or less constant packing friction all the way here, and then it starts to decrease here. So packing friction suddenly starts to change, and that's how you call it the free surface region. So you have a free surface region, then a bulk region in which packing density doesn't really change much, and then a base region where again you have something happening.
Interestingly, it looks more or less symmetric, right?
So this is just, this is just no, not necessarily. In this case, because I'm not plotting, it's not really symmetric. So free surface, you have packing frictions going closer to 0. Near the base, you don't have that. You have some. So I don't know where this number goes actually, but yeah, it's not symmetric. It's not symmetric at all. All right. So when remaining 10 minutes, what I'll do is, what we then tried to do is, so given the limitations that it doesn't explain, for example, the flow threshold dependence on height and the other non-local effects that you can observe, in the region it works, it is still defined only for monodisperse case. All right, so you have assumed a particular diameter of the grains or a particular density of the grains, and that is what seems to where it works. So what we have, during my PhD we tried to extend this to mixtures of grains. The simplest mixture that I could imagine was binary mixtures, particles differing either in density, which is represented by the colors here, or size, which is visible by the size itself, and based on that you can have either a D mixture, which means the particles differing in density, or a size mixture, particles differing in size, and you can have both size and density both being different, and that gives rise to two cases. The first one is what you call as S minus D, and the other one you call it as plus D. The signs essentially saying that your segregation effects are whether they are competing or cooperating, alright. And so by segregation what I mean is, okay, let me just show you a quick demo so that you understand what I mean, and then we can proceed with, that's okay. So I have a cylinder here, two different types of grains, alright. Although I have not necessarily kept it, so I mean since I already have this, I'll just maybe try to create a more generic situation. I'm not sure how much I will succeed. If I just keep doing this, so if no matter what initial condition you take, you have two different size particles. I just rotate the cylinder for some time, and you will end up getting, if you look at the large glass beads on the top, all the large glass beads come to the top. I don't know how many of you can see it, and if I disturb it they start rolling down, so I'm sorry, you will have to. So if you look at the fine sand is in the center, the periphery and the free surface, which you may not be able to see from there, is having primarily the large grains, alright, and the grains are sand and glass, the density difference is not so huge, so it's almost like a size segregating case, alright. So in this case your large grains come to the top. Contrast it with this. These grains are more or less same in size, one being sago, sabudana, and the other one being glass bead. Glass bead being heavy, almost 3 times density than sago, now comes to the periphery, whatever of it you can see, and the sago is now in the, comes in the center, and the sago in the periphery. So the high density thing comes in the periphery. Or if you just look at this region, what essentially we are saying is, if you look at a chute flow, what you are going to see is, if you had a mixture, you will have low density grains on the top, alright, and heavy density grains, alright. So this is because of density, but if I were to do in different size, as we saw, this will be large size and these will be small size. And so this is what I mean, that density case. So if your particle is of low density and large size and low density, segregation effects because of size and density are cooperating, and so you have S plus D system, both of these will try to go up, versus if you have the other case, they will be competing and you will have S minus D case, alright. So I'm not going to talk about segregation, but what I'm trying to, the only thing I'm trying to suggest is that it's possible to extend this effective friction law using a generalized inertial number, where my length scale is no longer the particle diameter itself, but a volume average particle diameter. Phi 1 is the volume concentration of the large particles, or one particle, and phi 2 is the other one, and you can define a volume average particle size and a volume average particle density, because those are the only two things which which are important, which are the particle properties in here. If I propose that, I can come up with a generalized inertial number and check whether this kind of mu I rheology helps me predict rheology of such mixtures as well. Mind you, these mixtures will show segregation like what we saw here. And so what we first show is results for systems differing in density. The symbols and the lines are velocity profiles for low density and high density. You see more or less the same velocity profile. This is the packing fraction concentration variation. Concentration of the heavy particle is 0 at the top, meaning no light particle, no heavy particle here, and all heavy particles concentrated in the base, so it's a very highly segregated situation. The packing fraction though shows very little variation, but more or less constant in the bulk. If you look at your shear rate shows sort of two regions, two linear regions with some connection in between, but if I try predicting the viscosity, which is shear stress, I can measure the shear stress from the simulation, shear rate from the simulations, and I plot the effective viscosity along with height for different theta. I use the same parameters that I had for my monodisperse case. So the particles have same restitution coefficient, same friction. The only thing that has changed is density and size. So then I can use the same model parameters, same value of mu1, mu2 and I0, And just to make sure that my other assumptions are not causing any difficulty in the verification, we are taking the pressure and gamma dot from the simulations, and then we'll see if we can use this in theory to get these also from theory. But to begin with, we'll just saying that whether the same rheological law works, and it seems like this complicated variation in viscosity, you have only only heavy particles here, only light particles here, can be captured pretty well. This can also be done for different size systems. Now with size systems, your large particles concentration is 1 at the free surface, primarily large particles at the top, smaller particles, most of the smaller particles are at the lower region. Your viscosity, if you look at, has changed significantly. It does depend on theta a bit, also depends on size and all, but same model parameters with generalized inertial number description seems to capture this pretty well. This is for a particular composition of 50-50. We have tried it from 10-90 all the way to 90-10 for different size ratios, 0.1, 0.5 to 2.5. So this is, for example, I mean, if you look at, this is for different compositions. You look at the viscosity variation, you see all sort of funny things happening, different composition, different size ratios, but it seems like the same parameters with generalized inertial number captures the rheology pretty well. And when you have the cooperating effect of segregation and density, so now you have large particles want to go up, are even lighter, so they would go more or less pretty quickly up, and so you see a very sharp transition, very thin region of intermixed region, otherwise pretty much segregated scenario. Lot of funny variation in the inertial number and whatnot, but your rheology still seems to work. The only thing you have to do is take the generalized definition of inertial number, and the same seems to be case for S minus D. In this case, because the two effects are competing, you have only one type of particles at the top and then a reasonably well mixed layer in most of the bulk, but this approach, the generalized inertial number, still seems to work. And so essentially what we are saying is your friction law doesn't seem to change unless I have changed the interaction between the particles. So if you are only changing density and size, because this mu1, these parameters do depend on, for example, if you change the friction coefficient of the particles. So your friction law doesn't really change, and your dilatancy law also seems to follow the same sort of thing, whether you have D system, S system, or S plus D system. Only thing is that you get some correction because of the packing. So when you have different size particles, they pack more efficiently than what you have a monodisperse system, which depends on the composition also. I mean, that you can sort of propose some fit, but essentially what we are saying is that it's possible to predict all observation. The only thing that is not there in the JFP model is that your normal stress difference are also important, not very significant in this case. So you are plotting the first normal stress difference divided by the shear rate and second normal stress difference divided by the shear rate as a function of inertial number for monodisperse case and for mixtures. And the summary is that your first normal stress difference seems to be, I mean, max value is 10% of the shear stress. The second normal stress difference is 30% of the shear stress. Not such a huge thing if you don't bother about it, and that's why people didn't bother about it. But if you do bother about it, your momentum balance equation has this del by del y of tau iy additionally chipping in, which, I mean, if you write the, I mean, if you use these relations for the normal stress difference to shear stress ratios, and along with that the tau xs, tau iy and tau zz should sum to 0, you can find that this tau iy is 1/15th or 2/30th of the shear stress. If I put that in my theoretical prediction, I do get much more improved prediction. So for example, I mean, this is my theory neglecting normal stress difference. I am plotting the value of mu, and when you account for normal stress difference, I do get my results slightly closer. Ignore the algorithm for the time being. My prediction, so the inertial number variation, it seems, is funny. The theory doesn't capture it. It still predicts you have a constant inertial number, but it seems to sort of, I mean, at least all other properties are coming out fine. So you see that your, for example, if you your velocity profiles show a bit off if you neglect normal stress difference. If you account for them, you get a pretty good match. Same with the shear rate. And so, okay, I think I'll stop here. So essentially what I have tried to show is that in the dense regime, this inertial number rheology seems to work for monodisperse case despite the limitations that we talked about, and it's also possible to extend it to different size mixtures, different density mixtures, even size and density combinations. I mean, we would like to extend it to sort of, I mean, multi-component, and just make sure that yes, you can indeed, I mean, it is possible to, if you couple this with a segregation model, it is possible to predict all this from momentum balance equation along with the constitutive relation and segregation which I did not have time to talk about. So what we have primarily looked at the granular statics part yesterday, some interesting effects what you observe in the fluid like dense flow regime, and one of the ways in which it can be understood pretty appropriately. The other sort of aspects of it probably what are not covered here, especially the segregation part, we can probably discuss it some other time if only time permits. Thank you.